So now what we're going to be talking about is indicators that indicate an acid, the presence of an acid, H plus ions, or the presence of a base, OH minus ions. And then we're going to be talking about something that you've never done before, single replacement reactions with metals placed in acid. And it's really good. And that's where most of your homework is going to come from. You'll have one question on indicators, but then you have a bunch of questions on that. But before we get to those two, we have to go over some of the bonus questions I gave you on the last video. Okay? So here are the two bonus questions that I gave you guys. NH3 plus H2O, we're going to make sure that NH3 is going to act like an acid, which means it's going to donate its H plus or bare proton to water. So here's what's going to happen. Since that's an acid, it's going to donate an H plus there. And so if it donates one there, on the other side, NH3 has one less H plus. So it's NH2 minus 1 because it lost a proton or an H plus. So what's left? Well, the H2O gained one, so that is H3O plus. Now, if you look at that, if I wanted my alternate acid-base pairs, remember the acid always has one more H than its base. So there's NH3, there's NH2. This has to be the acid. That has to be its base. What do you know about H3O plus? That's hydronium. That is always an acid. So that is A, and here is its base. So that's how that works. Okay, that's when ammonia is an acid. Now, ammonia can also be a base. So it can be both acid and base. So in this case, NH3 is a base. You know, if acids donate an H plus, an alternate base must receive an H plus. So NH3, if that's the base, it's receiving an H plus from the water. And if it receives an H plus on the other side, NH3 turns into this. And what is left? One H and one O from water, and that's this. So, that's what's happening, and now the acid-base pairs. There's NH3, there's NH4. That has one more. That has one more H than that. That's the acid. That's its base. H2O has two H's. OH, one H. That's the acid. That's the base. So that's how you work the two bonus. And my chem kids, if you were paying attention, your bonus was written word for word right in your packet. Some of you may have seen it, some of you may have not. All right, that's the first two bonus. The second bonus was, so the grape farmer soil needed to go from a pH of 6 to a pH of 4. So that means it's getting more acidic. Now your choices were 10 times more H pluses in 4, 20 times more H pluses in 4, 100 times more H pluses in 4, and 200 times more H pluses in 4. Now, this was on the Regents, like I said before, very few people got this right on the test. But, once again, if you were paying attention, that answer is right in your review book under Understanding pH in Chapter 8. So here's what happens. pH, when you go from a pH of 6 to a pH of 5, the pH of 5 has 10 times more H pluses. So if you go from a pH of 6 to a pH of 4, that would be 10 times and then 10 times. So going down 2 levels in pH would be 100 times more H pluses. If you went down from a pH of a 6 to a 3, that would be 10 times 10 times 10, so that would be 1,000 times more H pluses in water. If you were going back up, every time you went up 1, that would be 1/10 the amount of H pluses. So if you went up 2, it would be 1/10 times 1/10. There would be 1/100th times less H pluses. So that's how the pH scale works. All right, those were your bonus questions. Last video was on pH. And don't forget, pH is based on H plus ion concentration. But remember, there's no such thing as a free H plus floating around in water. The negative O from the water molecule pushes that H plus right on top of it by a coordinate covalent bond, making hydronium. Okay, but pH is based on acid. Remember? Okay, and 7 in the pH scale is neutral, and neutral is water, alcohol, and sugar. Anything below 7 is getting more acidic. Anything above 7 is getting more basic. And don't forget, if you go from a pH of 5 to a pH of 4, the pH of 4 has 10 times more H pluses in it. If you go from a pH of 5 to 3, it would be 10 times 10, it would be 100 times more H pluses. If you go the other way, well, then it would be 10 times less H pluses. Okay? So, this Table M in the New York reference table for New York State High School Chemistry is about indicators. They indicate if you have an acid or a base. There are a couple that I absolutely love. The first one I really like is litmus paper, because look at litmus paper. It goes from a pH of 4.5 to a pH of 8.3. So that means litmus paper covers not only the acid part of the pH scale, it also goes to the base part, and it goes from red to blue. So what that means is, for litmus paper, if the pH is below 7, the litmus paper is going to turn red. If the pH is above 7, the litmus paper is going to turn blue. So what we have is this. We have hydrochloric acid, and we have red litmus paper, and we have blue litmus paper. So let's put 1 drop of hydrochloric acid on there, 1 drop on here. So, watch. Hydrochloric acid has a pH lower than 7, so it must be red. So if you look at these two things, I hope you can see them, they both turned red. So acids turn red in red and blue litmus paper. All right? Okay, that's the first one. So next, with the litmus paper, this is NaOH. This is sodium hydroxide. This is a base. So let's put 1 drop on here. 1 drop on here. And if you look, the base turned litmus paper blue. Okay, right there. So red litmus paper and blue litmus paper both turned blue in a base. So, you know litmus paper goes from acid to base. I love that one. Also, another one I really like is Bromothymol Blue, because it does the same thing. It goes from a pH of 6, which is acidic, to a pH of 7, over 7, which is a base. So, here is bromothymol blue. I have an acid right here. So according to bromothymol blue, when I pour this acid in bromothymol blue, it should turn yellow. So let's see if it turns yellow. And it turned yellow. Okay? Now for the base, sodium hydroxide, bromothymol blue should turn blue in a base. Okay, so we have the bromothymol blue, we have sodium hydroxide. It should turn blue in a base. Let's see if it does. Okay, so now we know bromothymol blue turns yellow in an acid and blue in a base. So my question to you, and you're going to email me the answer, is if an acid turns yellow in bromothymol blue and a base turns blue, what color would neutral be? That is a question. I want you to write it down. What color would neutral be with bromothymol blue? And I want that answer. So the next indicator that I like also, so I like litmus paper, I like bromothymol blue because they go from acid to base. I also like phenolphthalein. Hard to spell, but I like phenolphthalein because look it, if phenolphthalein is below 8, which means acid, it's colorless. If it's above 8, it's going to turn pink. So here is an acid. So if I put phenolphthalein in there, it says it should be colorless. And phenolphthalein in an acid is colorless. Now, this is a base, NaOH. So let's see about this. It says that in a base, it should be pink. Yeah, that's pretty pink. So in a base, phenolphthalein turns pink. So here we go. In an acid, phenolphthalein is colorless. In a base, phenolphthalein is pink. Those are the three main indicators that I use in the acid-base chapter. So it's bromothymol blue because it can go from acid to base. It's litmus paper, acid to base, and it's phenolphthalein, acid to base. Okay? Thymol blue is mainly in the base area. Bromo green, mainly in the acid area. Methyl orange, mainly in the acid area. So this indicator chart tells you what it indicates, acid, base, or both. Okay, so the only question you have here is, with the bromothymol blue, if it turns an acid yellow and it turns a base blue, what's the neutral color? Okay, now we go into something brand new, and I really like this one. This is called Metals and Acids, and it's on reference table J. So what I'm going to do is I'm going to show you reference table J, and then we're going to do quite a few of these, and they're single replacement reactions. And I'll show you what the reactions actually are. And you will have homework in this part. So here's reference table J. It's called activity series. And it's already labeled the most active metals. They're usually from group 1 or group 2. Remember, group 1 or group 2 metals never found in nature alone because they're so reactive. So usually these are group 1 or group 2 metals all the way down to magnesium. Now, if we go down to here, these are the least active metals. So gold is the least active metal. But what I want you to do on your reference table J is I want you to circle H2. You circle H2. Now here's the deal. any metal above H2, when you put it in an acid, will make hydrogen gas when you put them together. We're going to do a couple of them. Any metal that's below H2, and there's only 3, copper, silver, and gold, will not react with any acid. That's why they're so expensive. Copper, silver, and gold, you put acid on them, nothing happens. But all the other metals above hydrogen gas, they react and produce hydrogen gas. All right? So, just these 3, copper, silver, and gold, nope, they don't work when you put acid on them. So when I put acid on lithium, rubidium, potassium, cesium, barium, the top metals, they go crazy. So any metal above H2, when you put it in an acid, will always produce hydrogen gas. And we're going to be talking, one of the first guys to actually do this was one of my heroes, Jacques Charles. Do you remember Charles' law? You better. It's a gas law. Remember? He was the dude with the balloons in like 1790. And he said that the volume of a gas is directly proportional to the Kelvin temperature. So as the temperature goes up, the volume goes up also. Okay, so we're going to be doing the experiment that he did in about 1790 today. All right, so now we're going to start with the single replacement reactions. Now, the first reaction we're going to do is potassium with hydrochloric acid. Now, if you look on your reference table, J, potassium is way up high. So obviously, we can't do this in lab because it would probably make an explosion. So watch how we do this. This is a single replacement reaction. So what's going to happen is the K is going to replace the H. And don't forget, any metal above H2, when you put it in an acid, will react to form hydrogen gas. So this is way up above H2. So watch what happens here. You're going to have to find your charges. Since potassium is by itself, it's neutral. And you know H is a positive and Cl is a minus. Okay? Now, K and H are going to replace each other. So over here, I get K plus Cl minus. And since it's a positive 1 and a minus 1, the sum of the oxidation states equals 0. We don't have to crisscross, do anything. Now, here's what else we get. And all my students, so every year, go, hey, wait a minute, there's only one H there. Why do you have 2 H's there? Because when you put a metal with an acid, if it's above H2 on table J, it always produces hydrogen gas. Now all you have to do is balance it. And don't forget, that arrow going up means the gas is given away. That's why this is only going one way. It can never be at equilibrium because you're losing a product. Remember, you have to have a closed system for equilibrium. All right, so now we have to balance the equation. So you're just looking, you have 2 H's. We're going to have to put a 2 right there. But then that makes 2 Cl's because the 2 blows through everything. So we got to put a 2 here. And if we put a 2 there, we make 2 Cl's, but we make 2 K's. So we have to put a 2 here. So that is your first single replacement reaction. And you're going to have a couple of these to do. All right? So here's your next one. this time we're putting calcium, which is a little bit lower on the chart, with nitric acid. And nitric acid's pretty strong. And remember, you got to find your charges. Well, the metal's by itself. The metal's always neutral if it's by itself. H is positive, and then this whole thing right here is negative. Okay, so same thing. If calcium is above H2 on reference table J, these two will replace each other. So that's what happens. So we have calcium, which is a +2, and then we have NO3, which is a -1. They don't match. Calcium wants to lose 2 electrons, while the nitrate polyatomic ion only wants to gain 1. So you got to crisscross. And remember, calcium is above hydrogen on table J, so it always produces hydrogen gas. Now, we got to balance it. Well, this one doesn't look too bad. You do have 2 hydrogens, so we only have 1 there, so we're going to have to put a 2 there. And that makes it pretty nice because remember that 2 blows through everything? 2 hydrogens, then it means we have 2 nitrate polyatomic ions. Well, guess what? We got 2 nitrate polyatomic ions right there. Everything's balanced. That was pretty easy. All right, now we're going to do the next one. Okay, so now we're getting really far down closer to H2 on reference table J. So when I put tin with phosphoric acid, it really doesn't work very well. It will give off some hydrogen gas, but nothing like the first 2 we did, because it's getting closer to H2 on reference table J. So, chart, tin, all by itself. Neutral. H, positive. PO4 -3. So now, single replacement again. So tin is going to replace hydrogen, and it's going to be this. Sn +2 PO4 -3. Now look at that. That does not match. It doesn't match at all. Remember, the sum of the oxidation states have to equal 0. So if it doesn't match, we have to crisscross. 2 goes here, and a 3 goes there. All right, so that's what that looks like. And now always, if the metal is above H2, you get H2 gas. But remember, we won't get very much H2 gas because tin is getting very close to H2 on reference table J. Now look at this crazy thing. We got to balance it. So the first thing I see is we have 2 PO4s. Well, we only have 1 PO4 there, so to get 2 PO4s, we put a 2 right there. Now that 2 blows through everything. So now how many hydrogens do we have? Well, 2 times, we got 6 hydrogens. So we have to come over here and put a 3. So now we have 6 hydrogens, 6 hydrogens, 2 phosphates, 2 phosphates, 3 tins, we only have 1 tin. So we have to put a 3 here, and we're good. Okay? So number 4. All right, silver, plus sulfuric acid. So silver, it's a metal by itself, that's neutral. H is a plus. SO4 is a -2. Now, if you didn't see it coming, look at reference table J. Silver is below H2. Any metal that's below H2 will not react when you put an acid on it. So, if you see this on one of my assignments, and you probably will, you do this. No reaction. There's no reaction because silver does not produce hydrogen gas with any acid. All right? Now, we're going to do my most favorite one because this one that we're going to do now involves Jacques Charles and Charles' law. Okay. So, this is what Jacques Charles in Paris did. I mean, we're talking 1790s. I don't know how he did it. He took, remember, all those ladies made all these quilts for him. And then what he did is he took pure rubber from rubber trees, dissolved it with something like turpentine, because they're both nonpolars, smeared it all over the inside of these quilts, and made like a balloon out of it, so it was airtight. And then what he did is he put a bunch of iron in a wooden barrel. And then he poured sulfuric acid on top of it, covered the barrel, and I don't know how he did this, but he made a hose going from the barrel to the balloon. So he was filling his balloon. Remember what I said, if the metal's above H2 on reference table J, it always produces hydrogen gas. He was filling his balloon with hydrogen gas, which is like 11 times lighter than air. So he filled his balloon with hydrogen gas, and it worked. So here's what Charles did. Fe neutral, H plus, -2, like that. So now, don't forget, I don't care how many H's on this side you have. When you make the reaction, you're always going to get hydrogen gas if the metal's above H2. So we're going to go like this, plus H2 gas given off. So what do we get here? We get Fe plus 2, and then we get SO4, and that's a -2. So if you look at that, +2, -2, we don't have to crisscross because the sum of the oxidation states equals 0. All right? And we don't even have to balance that reaction. It's all balanced. And this is what Jacques Charles did, and he filled his balloon with hydrogen. And like I said, really 1790s? So here is what the experiment is. Now, metal is pretty far, actually this metal, iron is pretty far down the chart, which means it doesn't react really well. So let's see. Here is some kind of weak acid, weak sulfuric acid. I put a lot of water in it, and here's some metal. I don't know if you can see it, but it's starting to bubble. But the bubbles are really taking their time going up. Because remember, iron is very close to H2, which means it doesn't really react very well. I'm sure Charles used some really concentrated sulfuric acid. This is very dilute sulfuric acid. Now, we're going to do one more experiment, and then I'm going to give you your homework. Magnesium, which is fairly high up the chart, and so we're going to go Mg plus, then we're going to use some nitric acid, HNO3 yields. Now, that's pretty far up the scale. So let's see about this one. We're going to put a little bit. This is dilute nitric. And if you see, watch, the stuff is really starting to bubble. Let me hold it this way. You can see the bubbles on top. So why is this reacting more than the iron? Because this is higher up on reference table J. And those bubbles, obviously, are hydrogen gas. Neutral, metal, this is plus, this is a minus, so it's Mg plus 2 NO3 minus 1. You know that doesn't work because they don't equal 0. Crisscross, 2 plus H2 gas given off. All right, so now once again we're going to have to try to balance this thing, and we have 2 nitrates, so we might as well put a 2 right there. That'll give us 2 nitrates, that'll give us 2 hydrogens. We already have 2 hydrogens, and that is perfect. That is a balanced reaction, and I know you can't feel it, but it is hot, so this most definitely is an exothermic reaction. Okay, now, the ones you are going to do for homework. We've given you a lot of examples, so these, I'm going to give you 3 for homework. So, obviously, you should copy these down. Number 1. First one is sodium and hydrochloric acid. Sodium's way up there. If we ever tried this, it would probably blow up. All right, so you're going to put down, obviously this is way above, so you can do hydrogen gas. You're going to do your single replacement, and then you're going to balance it. That is number 1. Number 2. So that's aluminum with nitric acid. And the final one, number 3, number 3 is copper plus phosphoric acid. So those are your 3. You're going to write them out and send them to me via email. And remember, you have a question about indicators. Once again, bromothymol blue, it's yellow in an acid, it's blue in a base. What color should neutral be? All right, we've only got a few more things left in the acid-base chapter. Thanks.